Good morning, friends. And we have already discussed about electrostatic potential, then the electrostatic potential because of many charges and due to continuous charge distribution. Now we are extending to the next topic, and in this topic we are going to discuss about conductors and different properties of conductors. In chapter 1, we classified elements into two major groups. One is called as conductor, other one is known as insulator. So, elements can be classified conductor and insulator. This conductors and insulator. Before going, let me see what is the topic. Its a topic is 2.9. This is 2.9 we are discussing. Dielectric also, one more thing there, but here we are, dielectric is nothing but it's an insulator. Conductor have free charge carriers, and these free charge carriers are nothing but electrons, negatively charged electrons. The electrons which are outermost or valence electron, they are free to move inside the conductor, but they are not allowed to leave the surface of the conductor. Now these electrons, they form, there is, suppose inside conductor this is the atom, nucleus is there, one electron is removed, this becomes positively charged, this is nucleus. So these electrons, they form gas cloud, they form one type of gas and they constantly collide with themselves as well as with these positively charged atoms. And therefore, they follow random motion. These positively charged atoms, less with electron but along with nucleus, they remain at their fixed position. When electrons drift from one point to other point, then the current set through the conductor. Now, for example, electric field is applied. This is electric field plus this is minus. Electric field direction is always from plus to minus, and electron is a negatively charged particle, so it will always drift towards the positive plate. So it's very clear that is the velocity of electron is opposite to that of the field direction. The electrons are always drifted opposite in direction to that of the electric field. So these are the few things which we know or we already studied it there. In case of electrolytic substances, both are charge carriers, positive Na and Cl minus, that is electrolytic. Here it is a positive sodium, here it is a negative chlorine, and both ions are charge carriers. Our point of discussion, in case of this one, current is due to these ions as well as these ions drift because of external electric field. But one more factor affects the current in electrolytic substances. These are chemical forces. We are not going to discuss this in here, but just I mentioned, in case of electrolytic substances, the conductivity or the current through them is bar because of cation and anion. So external electric field affects the current through them as well as the current is also affected by chemical forces. Now we are going to study these many properties of conductor. Let's see. 1, 2, 3, 4. Let us see what is the first property. Inside a conductor, electrostatic field is 0. Now, first property we are going to discuss. Inside the conductor, E is equal to 0. Let us see this one. This one is 2.91. Inside conductor, electrostatic field is 0. Electrostatic field is E is equal to 0 inside the conductor. Consider, this is the conductor. Now we all know that this conductor has free electrons to move. They can move from, or they can move anywhere inside the conductor, but they cannot leave the surface of the conductor. Now, for example, there is an electric field. It is applied in this field. This side it is a positive plate. This side it is a negative plate. Now, as soon as this field is applied, here this field is E. But what happens inside the conductor? All negative charges, they will come to this side. All positive charges, they will come to this side. Now this one, external electric field is from here to here. But this field is from here to here. This process of drifting goes on up to this E becomes this E. Both of them are opposite to each other. This one we can say it as E induced. This is E external. Now all these electrons will drift towards this one, and thereby there is a one field state. This process of drifting keeps on happening. Still, E external is equal to E induced. Both of them are inside the conductor. This E induced is there. So inside the conductor, this nullifies this. Therefore, it becomes E is equal to 0. Inside the conductor, E external plus E internal equal and opposite 0. Outside the conductor, only external field is there. And this drift of electron, movement of electron inside the conductor, is the main reason for electric field to be 0 inside the conductor. As the electrons are moving towards positive plate and the opposite electric field is induced, inside the conductor field is always 0. This is a very important result. Once again I say that inside the conductor electrostatic field is always 0. Let us discuss next point. Second point is 9.2. First point I have already discussed. 9.2. At the surface of the charged conductor, electrostatic field must be normal to the surface at every point. At the surface of the charged conductor. At the surface of a charged conductor. At the surface of charged conductor, electrostatic field is always normal to the surface at every point. It is very important. You can take surface. This is the surface. Suppose spherical surface, then this one is a normal to the surface. Field E is normal. Along radius, it is normal. But for time being, we consider that E is not normal. E is not normal. E is like this. We can resolve this E into 2. This one becomes normal component. It is and this becomes E parallel. If this E is not normal, making certain angle, then there are two components. One is a radial component, this one is known as a radial component, this one is a tangential component. Now this tangential component, E is nothing but force per unit charge. So this tangential component will trip electron, it will make electron to move on the surface. But all electrons are static, they are stationary. These are not moving. So whenever, in this case, at the surface of charged conductor, electrostatic field is always normal. Because all this situation is static. All electrons are static on the surface. They are not moving. So this component is 0. If this component is 0, total E is along this component. Or E is always normal to the surface of the conductor. Once again I say, we go by contradictory method. Initially we consider E is not normal. We can resolve it into two components, E radial, E tangential. This tangential component will make electrons to move on the surface of the conductor, but the charges are stationary. If the charges are stationary, it means that E parallel is 0. It also indicates that the total component of E is along this radial, which is normal to the surface. So at every point, at the surface of a charged conductor, electrostatic field is always normal to the surface at every point. This is the second point we have discussed. Let us come for third point. Third point is, the interior of a conductor can have no excess charge in the static situation. Interior of a conductor have no excess charge in the static situation. This is the conductor. First, we can see it as a neutral conductor. In case of neutral conductor, positive and negative charges are equal and they cancel out each other. But if excess charge is given, suppose that excess charge is given to the conductor, what is going to happen? First result, we know that E is equal to 0 inside. Here E is equal to 0. E is equal to 0, flux E dot ds is equal to 0. According to Gauss's law, flux is equal to Q divided by epsilon, which is equal to 0. It means that Q is equal to 0 inside. Then what happens to all the charges? Whatever charges you give it inside, these all charges are coming out on the surface. How do they come out of the surface? See, this is the conductor. Now, we have given some positive charges here. Then by induction, here negative charge comes. And outside there is a positive charge comes. This charge cancel out each other. And then all charges, they reside on outer surface of the conductor. So, the interior of conductor can have no excess charge inside. Even though you place charge inside the conductors, they appear on the surface of the conductor. This is very important result. Let us move to the next 2.4. Electrostatic potential is constant throughout the volume of the conductor and has the same value on its surface. Inside, this is the conductor. Now inside V, E is equal to 0. E is nothing but F by Q. Therefore, F is equal to 0. So no force inside. If there is a no force, this is one charge. From here to here, to go from here to here, no work is done. So between these 2 points, V1 and V2, there is no potential difference. V2 minus V1 is equal to 0. It indicates that V2 is equal to V1. It means that inside this one, on this inside the conductor, at all points, electrostatic potential is same. Now let us discuss on the surface of the conductor. We know that on the surface of the conductor, E is always normal. There is no tangential component. This tangential component is equal to 0. It means that on the surface of the conductor also, where the charge is going from this point to this point, no work is done on that one. Again here, V3 and V4. V4 minus V3 is equal to 0. It indicates V4 is equal to V3. So on the surface also, the potential at different points is same as that of the potential inside the conductor. These are 4 important properties of conductor. 2 more points from 2.9 we are going to discuss in next session. Once again I summarize, there are 4 properties. Inside the conductor, electrostatic field is 0. E is equal to 0 inside the conductor. At the surface of the charged conductor, electrostatic field must be normal to the surface at every point. The interior of a conductor can have no excess charge in the static situation, stationary situation. Electrostatic potential is constant throughout the volume of the conductor and has the same value on its surface. That's all. Thank you.